Hi class, in this video we will talk about the definition of the limit of a function. First, let f(x) is a function. C is a real number. Then the limit of the function f(x) as x approach C is L. This statement we say that the limit of f(x) as x approach C is L if when x gets closer and closer to C, we have f(x) becomes arbitrarily close to L. Okay. So we say that the limit of the function f(x) as x approaches C is L if when x gets closer and closer to C, f(x) becomes arbitrarily close to C. Close to L. And we can note this statement by limit f(x) x tends to C equals L. This definition is intuitive. You can imagine it. See here? When the variable x gets closer and closer to C, here we will have f(x) will get closer to L. Maybe from the left side, maybe from the right side, or maybe from both sides. Okay? And we will explain a little more about B here, arbitrarily close. So, what is arbitrarily close? Arbitrarily close means that you can write it as close as L as you want. Yes, as close to L as you want. What does it mean? It does mean that if you want the distance between f(x) and L less than 0.01, you can choose a value x near C so that this happens. And more, if you want f(x), the distance between f(x) and L less than 0.001, you can also choose a value x near C so that this happens. And in general, if you want the distance between f(x) and L less than a number of silent with very small but greater than 0, of course you can choose a value x near C enough so that this inequality holds. This is the definition, intuitive definition of the limit of a function. Yes. About the definition of limit of function, we have another definition, a formal definition using epsilon and delta, but I don't mention it here. You can see it in the textbook, okay? Now we come to some examples. some simple examples. We will try to use our definition to find some simple limit. First, we consider the limit of the function x cubed when x approaches to, what is it? You can see that, you can imagine, when x gets closer and closer to 2, maybe 2.01, 2.001, 2.0001, or from the left, minus 201, minus 2001, minus 20001, etc. When x gets closer and closer to 2, yes, you can see that fx is at x cubed. It will get closer and closer to what? Yes, its cubed will get closer and closer to what? You can use your calculator to calculate the value of x cubed at this value of x, and then give the conclusion. We can have that when x gets closer and closer to 2, x cubed will get closer and closer to 8 arbitrarily. So we have the value here is 8. In the next example, we will consider the limit of the trigonometric function psi x when x approaches 0. You can see that when x approaches 0 from two sides, the value of psi x will approach 0 too. You can use your calculator to check that arbitrarily. So you can see that the limit of the function psi x when x approaches 0 is 0. Next, we will come to the definition of limit of a function at infinity. In the first definition, we consider c, which is a real number. But how is c which is an infinity or minus infinity? If c is infinity or minus infinity, we have the new definition. We often call it limit of a function at infinity. Limit of a function at infinity. Okay. Let the function fx so the limit of the function fx as x increase without bound. Increase without bound is become larger and larger indefinitely. Okay? Is there? This state the limit of fx as s increase without bound itself means that when x becomes larger and larger, the value of f at x will become arbitrarily close to the number L. Okay? Arbitrarily close. We have explained before in the last definition. Now, we come to some example for you to clearly understand this definition more. First, we consider the limit of the function 1 over x when x tends to infinity. Oh, so sorry. this statement, the limit of f(x) at s increase with the power is L. You can note it by lim f(x) when x tends to infinity is L. Okay? And of course, you have a similar definition for c equals. For c is minus infinity. Okay, we can choose another color. We have a similar definition. The limit of f(s) as s decrease with the value is L if when s becomes smaller and smaller. Okay, f(s) become arbitrarily close to L, and of course, in this notation we must change infinity to minus infinity. Okay, and now we can see the example again. We consider the limit of the function 1 over x when x tends to infinity. Is that value is it? And if this is it, what is it? You can imagine, according to the definition, you can try to use its definition to find this limit. You can imagine when x becomes larger and larger, yes, x becomes larger and larger, 1 over s. How is it? It will become close and close and close to 0 arbitrarily. So this limit is 0, okay? And next, we can consider the limit of the exponential function when x tends to minus infinity. What is it? You can give some value of x. Try to imagine when s decrease and decrease, it becomes smaller and smaller. When s becomes smaller and smaller, the value of the exponential at x will become small. Will behave how? It will become closer and closer to 0 arbitrarily. So we have that this limit is 0. You can use your calculator to check this again. Maybe you can give it for x for some. You can give x some value. Maybe 10 to the power minus 2, 10 to the power minus 4, 10 to the power minus 6. Okay, and you can use your calculator to calculate e to 10 to the power minus 2. Oh, sorry, it will decrease, not this, sorry. You can use minus 10 to the power 2, minus 10 to the power 4, minus 10 to the power 6, and you can check the value of the exponential function at this value, and you can see that when x becomes smaller and smaller, the values of the exponential function at this value will become closer and closer to 0. Okay, so we have this limit is 0. Next, we will consider some more example. This example I have asked you to do in the slides and have given you the answer. In this video, I just try to explain why. First, we try to consider what is the limit of the exponential function when x tends to 0. Of course, you can use your calculator to check when x becomes closer and closer to 0. the value of the exponential function, the value of the exponential function will become closer and closer to 1 arbitrarily, so the reason is 1. And in the section B, we want to calculate the limit of the function of the inverse function of tan. Okay, when x tends to infinity. Again, you can use your calculator. You can assign to x some values with the logsure and logsures, maybe 10 to the power 2, 10 to the power 4, 10 to the power 6, etc. And you can calculate the value of the inverse function of tan. Inverse tan, okay, for inverse tan at 10.2, inverse tan at 10.4, inverse tan at 10.6. Okay, and you can see that. You can use the value to guess how the inverse tan function we have. And you can see that when s become larger and larger, the value of the inverse function of tan at x will become closer and closer to pi over 2. Yes, you can check that by your calculator. And by C you can see that we want to calculate the limit of the function log at 1, the function log 1 plus x log pair x tends to 0, and you can see that when x gets closer and closer to 0, the value of the value of Lonely pair 1 plus x will get closer and closer to 0. Okay, and then D you can see that when x become larger and larger, the value of so the function e to the power of minus x will have the value become closer and closer to 0 arbitrarily. So you can see that this limit is 0, and I give the answer in the slide that D and E means that first let me show you what is E is the limit of the function psi s when s tends to infinity. And I give you the answers D and E. D and E here means does not exist. Yes, does not exist. So why do we say that the limit of psi x when s tends to infinity does not exist? Why we can say that? You can try. You can assign to some values, which is order, larger and larger, and you can use a calculator to calculate the value of psi sum s, and you can see that you didn't recognize any regulation. Yes, any rule. You can see that it has not. You can see that this value does not get closer, and this value don't get closer and closer to a value L, which we want. But it's just our guess for some values. Yes. For the answer of this conclusions, you should use a graph of the function size. Okay, you see right here. You can see the graph of the function size. 0 x y y is psi x. Here the graph of the function psi x, okay? You can see this is the graph of psi x. And you can see here, we can do x here. Okay, x here. And we have a value x here in the graph. We have a point m. Okay, here's equal 1 and here is minus 1. And in this point m, and you can see y here, and y here is has value size. Okay, what will happen when it's become larger and larger? Yes, you can see here. When x become larger and larger, m will move along the graph. Okay, m will move along the graph. And of course, when m move along the graph, y will change. How can y change? How can y change? Can you see? X become larger and larger, and m move along the graph of size. The value of y will change. It will change between minus 1 and 1. How can it change? You can see, yes, in this axis, this is minus 1, this 1 and the 0. You can see when m moving along the graph. Yes, first y will move from 0 to 1. Now we may choose other color. 0 to 1, and then it will move from 1 to 0 to minus 1, and then we will come from minus 1 to 1, and then it will come 1 to minus 1, and then it will come from minus 1 to 1. It repeated infinitely. Comes from 1 to minus 1, minus 1 to 1, 1 to minus 1, minus 1 to 1, 1 to minus 1, minus 1 to 1, 1 to minus 1, minus 1 to 1. And so, with this, what is the number? It will get closer and closer arbitrarily. Is it 1? No. You can see that. When you stay at 1, sometimes you will see that it will get closer to you, and then it will go away. How about minus 1? You can see that when you stay at minus 1, you can see that y sometimes get closer to you, and then will go away. And of course 0, similarly. So you can see that y is not get closer and closer and closer arbitrarily to some arbitrary to some number, to any number, when x get larger and larger. So you can see that the limit of the function psi s when x tends to infinity does not exist. Similarly, you can have that the limit of the function cos psi x when x tends to infinity is also does not exist. In this video, we have talked about the limit of a function, the limit of a function at infinity, and we have give some examples of using the definition to find the limit. If you have any question, don't hesitate to comment below the video. I will answer. if I can't. Thank you for watching.